Imagine hiking high into the mountains of Utah. Ahead of you is a broad slope covered in gray boulders. No shining wall of ice, no blue crevasses, no obvious glacier at all. It looks like nothing more than a giant pile of broken rock sitting beneath a steep mountain. But if you could cut through that rubble, you would find something completely different. Ice. Not a thin frozen layer. In places, the buried ice may extend roughly 37 meters or 120 feet beneath the rocks. And when researchers recently mapped one of these strange formations beneath Mount Timpanogos, they found that it was about 83% ice by volume. The mountain had been hiding a glacier in plain sight. And this is not just one unusual patch of frozen ground. Utah alone has 836 documented rock glaciers. Around the world, scientists know of roughly 50,000. Using their new measurements, researchers estimate that these hidden glaciers could collectively contain around 48 cubic kilometers of water. That is 48 billion metric tons of water stored inside landscapes that from above can look like piles of rubble. The discovery raises a surprisingly simple question. How do you hide a glacier under a mountain of rocks? To answer that, picture a normal glacier. Snow accumulates high in the mountains, more snow falls than melts. The weight compresses the snow into ice, and eventually that mass begins creeping downhill under its own weight. A rock glacier also moves downhill. But its surface looks completely different. Instead of exposed white ice, it is covered by a thick armor of boulders, gravel, and broken rock. From the surface, you may see ridges and lobes that resemble frozen waves of debris, but underneath, ice can fill much of the interior. The rocks act almost like insulation. Sunlight heats the surface, but the debris layer slows the transfer of that heat into the ice below. As a result, buried ice can survive in places where exposed ice would melt much faster. It is almost like putting a thick blanket over an enormous block of ice. Except the blanket is made of stone. Mount Timpanogos provided researchers with an ideal place to investigate one. For years, people referred to an icy feature beneath the mountain as the Timpanogos Glacier. But researchers now recognize the larger formation as a rock glacier, one whose true interior could not simply be judged from the surface. The problem was obvious. Satellite images can show the footprint of a rock glacier. They can tell you where it begins and ends. But they cannot easily tell you how much of the interior is rock, how much is ice, or exactly how deep the buried ice extends. You could drill holes into it, but a few holes would only tell you what exists at a few points. Researchers wanted something closer to a three-dimensional scan, so they used gravity. In 2024, geologist Bronson Sivajanovic and colleagues carried a highly sensitive gravimeter across the Timpanogos rock glacier. Over 6 field trips, they collected measurements at 232 different locations, spaced roughly 25 meters apart. A gravimeter measures extremely small changes in gravitational acceleration. Normally, we think of gravity as essentially constant when standing on Earth. But the mass beneath your feet matters. Rock is denser than ice. So if you stand above a thick body of buried ice, there is slightly less mass below you than there would be if the same volume were solid rock. That difference produces a tiny change in the local gravitational field, tiny enough that a human could never feel it. But sensitive instruments can measure it. Imagine replacing a huge block of stone underground with a block of ice of exactly the same size. Nothing changes on the surface, but the ice weighs much less. Gravity above that location becomes very slightly weaker. By walking across the rock glacier and repeatedly measuring those differences, the researchers could begin reconstructing the hidden shape below. But it was not as simple as finding weak gravity and calling it ice. The measurements had to be corrected for elevation, for surrounding mountains, for latitude, and even for gravitational effects associated with the positions of the sun and moon. Only after removing those influences could the team isolate the signal created by the structure underneath them. Then they used a three-dimensional Bayesian inversion. The name sounds complicated, but the basic idea is easier to visualize. Imagine you are given hundreds of gravity measurements across a mountain slope. You know roughly how dense the local rocks are. You know how dense ice is. Now you ask a computer to generate possible underground structures that could produce the measurements you observed. Some possible shapes fit badly. Others fit much better. By repeatedly testing different internal structures, the researchers can build a probability map showing where buried ice is most likely located and how thick it probably is. It is something like a CT scan of a mountain, except instead of X-rays passing through a body, the researchers used tiny variations in Earth's gravity. The resulting picture was striking. The Timpanogos rock glacier contained about 1.5 million cubic meters of frozen water. That is enough to fill roughly 600 Olympic swimming pools. It is also roughly comparable in volume to the Great Pyramid of Giza. And the estimated composition was far more ice-rich than its rocky surface suggested, around 83% ice and only 17% loose rock. Now comes the twist. It would be easy to assume this hidden glacier is simply a leftover from the last ice age. A frozen remnant that has somehow survived for tens of thousands of years beneath a protective cover of rocks. But another study of the same system suggests the story is different. The Timpanogos rock glacier appears to have accumulated after the great ice age glaciers in the area retreated. Instead of being merely a dying piece of an ancient glacier, it may still be maintained by a process happening on the mountain today. Look upward from the rock glacier and you find steep mountain walls. Those walls constantly weather and break apart. Pieces of rock fall downhill. Snow also accumulates below them. When rockfall buries persistent patches of snow before they melt, the debris protects the snow from summer heat. More snow arrives. More rock falls. Over repeated seasons, buried snow can become incorporated into the slowly moving mass. The researchers' model suggests that this combination of snow accumulation and falling debris helps feed the rock glacier. The strange object is therefore neither simply a pile of rocks, nor an ordinary glacier. It is a slowly moving system built from ice and debris interacting over thousands of years. And it really does move. Like conventional glaciers, rock glaciers deform and creep downhill under gravity, although often very slowly. The thick rocky shell can make that motion hard to notice from the ground. A hiker may step across what appears to be a permanent field of boulders, without realizing the entire landscape beneath them is gradually flowing. This is one reason rock glaciers are easy to overlook. We are trained to recognize glaciers by appearance. White ice, snow, crevasses. But a glacier-like body does not need to look icy on the surface. Sometimes the ice is almost completely hidden. The researchers then took their result from Mount Timpanogos and asked a much bigger question. Could the relationship between surface area and buried ice help estimate water stored in rock glaciers elsewhere? From their measurements, they developed a scaling relationship connecting the visible footprint of a rock glacier with its likely ice volume. Applying that relationship more broadly produced a remarkable estimate. The approximately 50,000 known rock glaciers around the world may hold about 48 gigatons of water. 1 gigaton of water is 1 cubic kilometer. So we are talking about roughly 48 cubic kilometers of water locked inside these rocky mountain structures. Utah's rock glaciers alone may store around 1 gigaton. That is roughly 266 billion gallons of water. And this matters especially because Utah is dry. Much of its water supply depends on mountain snow. Snow falls during winter, melts during spring and summer, and feeds streams, reservoirs, and cities. But as temperatures rise, mountain snowpacks can shrink and melt earlier. That creates a timing problem. Water may arrive when it is less needed and become scarce during the hot, dry part of late summer. Rock glaciers behave differently. Their rocky covering protects the ice. That does not make them immune to climate change. They can still warm, melt, and change. But thick debris means their internal ice can respond more slowly than an exposed glacier or seasonal snowpack. They may continue releasing cold meltwater long after ordinary snow has disappeared from surrounding slopes. Previous research in Utah's Uinta Mountains has suggested that rock glacier meltwater can contribute as much as roughly a quarter of late summer runoff in some high alpine catchments. That means a landscape that looks dry and rocky may quietly be feeding streams during the part of the year when water is most valuable. The significance becomes clearer around Salt Lake City. About a quarter of the city's water supply comes from Big and Little Cottonwood canyons. Those two watersheds contain around 70 rock glaciers. Scientists do not yet know exactly how much of the city's water ultimately comes from them. But it means some fraction of a major urban water supply may already be passing through hidden mountain ice that most people never see. And this is where the story becomes larger than Utah. Mountain regions around the world contain rock glaciers. The Alps, the Andes, the Himalayas, North America, Central Asia, Many occur in regions where communities depend heavily on mountain water. If exposed glaciers and snowpacks continue declining, the importance of these slower, protected ice reserves could increase. But before water managers can include them in long-term planning, scientists need to know how much water they actually contain. And until now, that has been remarkably difficult to measure. One rock glacier might contain mostly debris with relatively little ice. Another may be ice-rich like Timpanogos. Looking at their surfaces alone cannot always tell you which is which. That is why the gravity technique matters. It provides a way to investigate the hidden interior without excavating an entire mountain. There is also a warning inside the global estimate. The researchers have not individually measured all 50,000 rock glaciers on Earth. The 48 gigaton number is an extrapolation based on the relationship developed from the detailed Timpanogos measurements. Different mountain ranges have different climates, geology and formation histories. Some rock glaciers may contain less ice. Others could contain more. So 48 cubic kilometers should be treated as an estimate, not as a direct global inventory. More field measurements are needed to find out how well the new relationship works across different environments. But even the uncertainty reveals how little we know about an important part of Earth's frozen water. We have mapped enormous glaciers from satellites. We monitor polar ice sheets from space. We can measure seasonal snow over entire continents. Yet some frozen reservoirs sit beneath mountain trails and fields of loose boulders, largely hidden because they do not look the way we expect ice to look. That is what makes Timpanogos such a useful example. Stand on top of it and you see gray rocks. Measure its gravity and another landscape appears. A buried mass of ice tens of meters thick. A slowly moving frozen reservoir. Hundreds of swimming pools of water hiding underneath your feet. And perhaps the most surprising part is that the rocks covering it, the feature that makes the glacier almost invisible, may also be the reason so much of its ice is still there. The mountain hides the glacier, and by hiding it, the mountain protects it.